Now we go to Pareto. Okay, same concept. Plus, we try to transform from the Pareto. We try to transform to the exponential. From there, you can get the parameter. Okay, so here we go.
Pareto distribution. Pareto distribution is a transform exponential distribution. If X has a Pareto distribution with parameters alpha and unknown theta, then log X plus theta divided by theta has an exponential distribution with mean of alpha to the power of -1. Thus, the MLE of alpha is given by this result. Pareto distribution proof. Suppose the random variable X is Pareto distributed with parameters alpha and theta, where theta is known. Let Y be a random variable such that Y is equal to log X plus theta divided by theta.
Okay, so this formula is important for Pareto, transformation of Pareto. But do not worry, I say usually this is given in exam. Carry on.
Then, by transformation, we have the following. That is, the CDF at the result Y based on random variable Y, which is equals to the probability of random variable Y, which is less or equals to the Y value. And now we try to substitute Y as this, then we will have this result. And rearrange, then X plus theta divided by theta, which is less or equals to e to the power of Y. And arrange this again, we will have the probability for the random variable X, which is less or equal to theta times e to the power of Y minus 1. And this is obvious, which is equal to the CDF at this value based on X. Now, since X is Pareto distributed, then this CDF, we can get the formula from table C, which is equal to 1 minus the parameter theta divided by this X value and plus the parameter theta to the power of alpha, and this theta will be eliminated, and so we have 1 minus 1 over e to the power of alpha y, and this is equal to 1 minus exponential to the power of -y divided by alpha to the power of -1. And obviously, this is a CDF of the exponential. And in other words, this random variable y, that is log x plus theta divided by theta, which is exponential distributed with the parameter of alpha to the power of -1. So we complete the proof. So since y is exponentially distributed with this parameter, therefore this parameter alpha to the power of -1, which is equals to the sample mean, that is the summation of log xi plus theta divided by theta when I takes from 1 to n and divided by the sample size n. So in other words, alpha, which is equals to n divided by summation of log xi plus theta divided by theta when I takes from 1 to n. So now we try to expand the denominator, and so we will have log x1 plus theta divided by theta plus log x2 plus theta divided by theta plus until log xn plus theta divided by theta. So this can be simplified as a product of log, that is log x1 plus theta divided by theta multiply x2 plus theta divided by theta and multiply until xn plus theta divided by theta. Therefore, this is equal to, this can be simplified as log product of xi plus theta divided by theta when I takes from 1 to n, and hence we prove the result.
Okay, class. The solution maybe can stop at this summation here on top here. Okay, but usually, of course, this is much more meaningful compared to this, because if you stop at here, you still have to, once you substitute your x value, you still need to sum up. You need to calculate, you can see, because this summation, right, you have to calculate the sum of the log many times. Okay, if you simplify this log, actually is a log product of this term. This is much more easy, okay, because you sum up all this, you take the one time of log. Here you'll pass many time of log. Up to you, class. Okay, some of the book they stop at here. Okay, some of the book they stop at here. Okay, but of course I prefer this one, the last one, because we only press one time log. I only calculate the sum of this, the xi plus theta divided by theta. I sum up all this. When I get the final result, I press only one time log. Okay, compared to here, you have to press many times of log. Then only you can sum up. So you can compare. Okay, you will know which is easier and faster. So again, you can see the whole process here. That is, I want to transform from the Pareto. I must this equation. As I say, class, if you're smart, okay, actually this formula we can trace. You can trace from table C, but here I have no time to explain to you, and maybe you no need to understand also. Okay, I can trace, class. I will know what formula I should use. Okay, but I say already, usually this is given in exam. Okay, so from this equation here, class, you just substitute. Eventually, you can see it is a exponential distribution, right? This exponential. Okay, under this just now this equation here, you just simplify. Eventually, is exponential. What is exponential? Then I know already. Okay, this whole thing actually is exponential distributed. Log x plus theta over theta is exponentially distributed with the parameter 1 over alpha. So this 1 over alpha, then I can use the MLE from the exponential. You can see the pattern. The pattern of x here, I just copy on it. From the capital X, I just change the small letter x, because this x, capital X is a random variable. This small letter x actually is the value. Okay, so this 1 over alpha is a parameter for exponential. But if I convert to alpha, then this is a parameter of the Pareto. Okay, so we have proof. So the next is example.
Example 13. A random sample of 8 values from a distribution of x, which is given as follows. Assuming that x is from a Pareto distribution with parameter theta is 10, find the maximum likelihood estimate of alpha. So our aim is to find the maximum likelihood estimate of alpha, that is this. And hence, we have to use the formula we have proven. Solution for example 13. Given a random variable x which is Pareto distributed with the parameters alpha and theta which is given by 10, where the 8th observation is given as follows.
Okay,
Hence,
this one also I jump a little bit because I think you should know how to substitute. Okay, I want to calculate for the alpha. I need to know what is my alpha, this parameter of Pareto. I have to use this formula. Okay, so I substitute all the observation into this formula. I will get the alpha value. Okay, so you can see I use this formula. I calculate, right? I calculate everything. I only press one time block. Okay, so I will have this alpha. This is my solution, right? So it's much more easy for me to calculate if I use this formula. Can you imagine if you use just now the summation? Okay, you have to take the log every time, log for everything, sum out, and then it's the result. That one I take long time. Okay, so up to you. You will get the same answer. So this is the parameter value for the alpha. Okay, just substitute into the formula. Okay, so this is example 16. I need to go to two more. We move to next. Okay, so we go to single parameter Pareto distribution now. Okay, we can calculate many class under transformation.
single Pareto distribution. Single Pareto distribution is a transform exponential distribution. If X has a single Pareto distribution with parameter alpha and a known theta, then log X divided by theta has an exponential distribution with the mean of alpha to the power of -1. Thus, the MLE of alpha is given by this result. Single parameter Pareto distribution. Proof. Suppose a random variable X is single parameter Pareto distributed with parameters alpha and theta, where theta is known. Let Y be a random variable such that Y is equal to log X divided by theta. Then, by transformation, we have the following. The CDF at the Y value based on random variable Y, which is equals to the probability of random variable Y, which is less or equals to the Y value. And now we substitute the Y as log X divided by theta, which is less or equal to Y. And so, X divided by theta, which is less or equals to exponential to the power of Y. So, this is equal to the probability of X, which is less or equals to theta multiply e to the power of Y. So obviously, this is equal to the CDF at theta times e to the power of Y based on X. And since X is single parameter Pareto distributed, therefore, this is equal to 1 minus parameter theta divided by the X value to the power of alpha. And we simplify, theta is eliminated, and so this is equals to 1 minus 1 divided by e to the power of alpha y, or we say this is 1 minus e to the power of -y divided by alpha to the power of -1. So obviously, this y is exponential distributed. So in other words, we say that this log x divided by theta, which is exponential distributed with the parameter alpha to the power of -1. And hence we prove the result. Now, Since this is exponentially distributed, therefore, this parameter alpha to the power of -1, which is equals to the sample mean, that is a summation of this log xi divided by theta when I takes from 1 to n divided by the sample size n. In other words, alpha is equal to n divided by summation of log xi divided by theta when I takes from 1 to n. And now we try to expand the denominator, so we will have log x1 divided by theta plus log x2 divided by theta plus until log xn divided by theta. And this can be simplified as log x1 divided by theta multiply x2 divided by theta and multiply until xn divided by theta. So obviously, this is equals to log xi divided by theta when I takes from 1 to n. And so we prove the result.
This is the product, okay, not the summation. So that's why I replace it. Okay, so this is a summation that you add up, right? But inside this bracket is a product. Product is the notation is something like pi. Okay, this notation is sigma. We call sigma notation. Sigma notation is for the summation. The pi notation is for the product. Okay, so we have proven the formula. Use the same concept. Okay, same concept. Transformation. That the keywords is from this, right? The y equal to log x divided by theta. Okay, so I give you some hints to get this. Let's say you can trace from here. You can take the table C. You can trace back, then you can see at last this is the y. Okay, so that's why I say you can check from your y. Let's say in a certain examination maybe they didn't give the formula. Actually, you can trace. You come to the last step here. You go backwards. You go backwards. At last, you can see this is your y log x. You will get log x over theta. Okay. Well, of course, don't worry. In my paper, I will give. I won't ask you to trace or memorize. Okay, no worry. Okay, so once you have proven this is an exponential, then the rest should be no problem. Right? You will get the parameters for 1 over alpha. Okay, 1 over alpha is a parameter for the exponential. You convert back to the alpha, then you will get this is the parameter for the Pareto. Transformation actually have a limitation, class. You only allowed to calculate one parameters. Okay, because Pareto we have two single parameter Pareto we have two parameter. Okay, we have two parameter, but you only allowed to calculate one. In other words, the other one must be given. Okay, if you don't give me the value of another one, then I cannot solve by transformation. Okay, because the transformation, you can see the last result here, I need to know what is my theta value, right? If I don't know the theta value, how can I find the alpha? You must let me know what's the theta value. Okay, and I know the observation. I know I must know what's the theta. Otherwise, I cannot find the alpha. Okay, so this is a limitation for the transformation. Okay, so next we can go to the example. So example also I will skip.
Example 14. From the data given in example 13, assuming that x is from a single parameter Pareto distribution with parameter theta is 10, find the maximum likelihood estimate of alpha. So from example 13, we have this 8 observation. And from this 8 observation here, we need to find the maximum likelihood estimate of alpha, that is to find this estimate of parameter of alpha by applying this formula where n is 8. Solution for example 14.
Okay, here I jump step a bit. So just apply the, okay, all the observation apply, okay, and get the product of this, calculate with the log. Then at last you get this, the alpha is 17, actually about 17. Okay, just apply only the observation once you know the formula. Okay, so it's quite easy. Okay, let me go to the last one. Okay, now we go to log normal. Log normal distribution is a bit different, class. Okay, the formula is a bit different. The concept also a little bit different, but more or less are the same. Okay, so here we go.
Log normal distribution. The log normal distribution is a transform normal distribution. If x has a normal distribution with parameters mu and sigma, then log x has a log normal distribution with the same parameters mu and sigma. To calculate the maximum likelihood estimators of the parameters mu and sigma of a log normal distribution, undo the transformation same as the estimates found from the method of moments. For a log normal distribution with parameters mu and sigma, then respective MLE of mu and sigma square is given by the following formulas.
Just now a bit jump already, I think. Okay, so when you do the transformation for log normal distribution, so the MA for log normal were not the same estimate found from the methods of moment. Okay, just I think I don't know what happened, jump already. Okay, so carry on.
Log normal distribution. Proof. Suppose the random variable x is normal distributed with the parameters mu and sigma square, then based on MLE, the estimate of mu and sigma square is given by these formulas. Let y be a random variable such that y is log x. Then by transformation we have the following, that is the CDF at y value based on random variable y, which is equals to the probability of random variable y, which is less or equals to the y value. And now we try to substitute the y as log x, and this will be equal to x, which is less or equals to e to the power of y. Obviously, this is a standard normal CDF at e to the power of y. Since y is equal to log x, therefore e to the power of y, which is equal to x. So in other words, this y equal to log x, which is log normal distributed with the same parameter mu and sigma square. So we complete the proof.
Okay, so the proof is a bit different from the previous because this one is a log normal. Log normal and standard normal very close connection. Okay, because they share the same parameters. Okay, so you do the same thing. Only the last step here, you convert back to the x. From this y terms here, you convert back to the x. Then we use the same parameters, but only is at first our x is normal distributed. Now is a log x log normal. Okay, something like both sides. What I mean is here. What I mean is here, our X is log normal distributed. Okay, so both sides you take log something like log X, log normal, something like this. Okay, so only the proof for log normal is a bit different. Okay, compared to the rest. Okay, so we have this proven the log normal distribution share the parameters from the normal. Okay, but only the calculation is different. Let's get it on.
Now, hence, the estimate of this parameter mu, which is equals to the sample mean, that is the summation of the observation, which is replaced by the log xi when I take from 1 to n divided by n. And the sigma square, which is equals to this when the observation xi replaced by the log x. So we will have the summation of log xi minus the mean square when I takes from 1 to n divided by the sample size n. And hence we prove the result.
Okay, it's clear, right? When X is normal distributed, this mu and sigma under this row moment formula. But when it's a log X, then this X here, we just follow the pattern. The X just replaced by the log X. Then you can see this is a log X, this is log X. Okay, so this is how they calculate the parameters for the log normal. Okay, next.
Example 15. A random sample of 5 loss values from the distribution of X is given as follows. Assume that the sample is from a log normal distribution. Find the maximum likelihood estimate of mu and sigma square. So our aim is to estimate the mu and this sigma square, and hence to get this result we can use this formula. Solution for example 15.
Okay, I skip some step here. We want to calculate the mu and the sigma. So very simple. You just use a formula. Okay. So this is answer for the mu. Let me look at the question first. Sample is given by this. Assume that this sample is log normal distributed. Okay, I want to find the mu and sigma square. Okay, so our X actually is log normal. So this one actually is log normal. I think I overlooked already. Okay, so I hope my solution is correct. Okay, let me check. You hold on, let me check. Yeah, in my solution I given to you the notes. Actually I type log normal. Okay, but here I overlook. I put normal. Okay, please, class. I hope you see my mouse moving. This X is log normal distributed instead of normal. I make a mistake here. Okay, so I need to calculate what's the mu and sigma square. So you just use the formula. Okay, place the observation and take the log. After that, sum up. Then you get the solution for the mu. Okay, so the mu actually is about 1.34. Okay, this mu is a parameter for the log normal. Next is the sigma. Again, use the formula. Okay, substitute all the observation. Okay, you calculate, you will have this sigma square is 0.19. Now, until today class, normal and log normal, you must understand they this sigma square in normal distribution, I'm talking, is a variance, right? It's a variance. And this mu in normal distribution is mean, is the average. But in log normal, the mu is not the mean. The sigma square is not the variance. If you want to know the variance, if you want to know the mean, go to table C. Look at the log normal, you will get the formula. Okay, you will get the formula, you can calculate the variance. Take the second row moment minus the first moment square. Here you will get it. Okay, because some students still dreaming. Okay. Okay, so I have done this chapter 4 class. Next week we will go to the last chapter, is chapter 5. Okay. So tomorrow we have tutorial. So we try to